Hey, my name is Andrew. I'm a master's degree student at the Technion, and I work on formal verification. I'm developing a piece of software that is meant to formally verify hardware verification problems or formally verify hardware designs. And so, and part of my research, I made a parser for end inverter graphs and inverter graph files, and I just wanted to share what they are for any starting students that want to get into hardware verification and have a tough time of understanding the underlying problem that we're trying to solve. So this is basically like an introduction to what goes on here. I'm assuming some familiarity with hardware architectures from the listener. So if you guys don't know what that is, there are multiple very good resources on YouTube. So just it'll be fine. An inverter graph is a graph that is meant to represent a hardware architecture. And the way this happens is by having four nodes in four types of nodes, in the graph. AND nodes, latches, inputs, and just a constant zero node or just a ground node. And edges can either be negated or non-negated. Negated means that they have a NOT gate on them. Non-negated means that they do not have a NOT gate on them. And so if you take, for example, this graph right here, or this circuit right here, the underlying graph would be the same, except we turn the NOT gates into just negated edges. And this is basically it. This is a node. It's basically the node that has the type constant zero. It's the only node that has that type. This is an input node. This is a latch node. And this is a latch node as well, and so are these two. This is a AND node, and this and this. So basically it's a simple layout. It's not really complicated at all. This layout was developed in order to allow for hardware model checking competitions to happen. I think specifically HWMCC in 2007, if I'm not wrong. They developed this file format in order to give the problems to the solvers and for the solvers to have like the same API. And then this was further developed by version 1.9, which added some extra features, and later on they created another file format for word level model checking, which is called btor, but we won't talk about it here. And most of the resources I took in order to create this video are from this website. This has the original explanations, what happened in version 1.9. Some repository that works with AIG files turns them into other things. It's really neat. It's really nice to see. And so this is like just my references page all in one. And this is the repo that they have that they made, and the format readme here. The format file here has the explanations of what an AIG file is, basically all of the stuff that we talk about, except that this format file does not have version 1.9 in it, and the additions to 1.9 are in another paper that was published later, which I've also linked to. In this slide, I'm basically putting it all together and in a video, so you can go through them in like 15 minutes or 20 minutes, however long this video turns out to be. Okay, so the rules for AIG files. Take a deep breath because we're going to get started. Every node in the graph has two identifiers, a signal number and a wire number. The signal number is just half of the wire number. Okay, so let me just clarify why that is. A signal number is basically an index. It's a unique identifier. A wire number is to talk about, it talks about connections more. So if you would have an input to a latch, that input can either be one of like connected directly with a non-negated edge to each node in the graph, or it can be negated with each one. And so you would differentiate using even and non-even numbers. And so you'd use wire numbers, if that makes sense. So signal number 0 is reserved to the ground in all AIG files. It always exists no matter what. And then you have input signals that go from 1 until number of inputs. If number of inputs is 1, then we just have like the one thing, and if it's 0, then this entire range doesn't exist, more or less. And so, like, that's what I meant to do. I'm not sure if this conveys it, but basically, if you have 0 inputs, then there's just no inputs, no input signals. Latches and flip-flops go for from number of inputs plus 1. Okay, so we start from like number of inputs and we add 1, so we go like the chunk that's after it, and the chunk is of size number of latches. So we just go, for example, if I had 2 inputs and 3 latches, let's say, then the signal 0 would go to the ground state, the ground node, sorry. And then signal 1 and signal 2 would be inputs, sorry. And then signal 3, 4, and 5 would be latches. And then 6, 7, 8, and onwards would be AND gates. Okay, that's what I stated here. And then all AND gates are 2 input AND gates because that's all we need, and also it's very convenient. And you may only use inputs that are lower, that have a lower signal. So that means an AND gate can't have an input that has a wire number that is greater than its own, or even it can be even equal to its own. What does this allow? This means that you cannot have cycles in the AND logic, because if you had a cycle, then this this feature would not hold for one of the AND gates. And yeah, there are multiple sections. We'll talk about them later. It really depends on what's in the AND gate, what's in the graph, and what's not in the graph. It really depends on the versioning as well. It's kind of complicated. And then even wires are non-negated connections, and then odd wires are negated. Okay, so if a latch had input 0, then it would be connected directly to the ground. If it had input 1, then it would be connected to a negated version of the ground. Okay, so the same is true for AND gates, for example. Now, the first line of an AIG file starts with this behemoth right here, such that with the word AIG or AAG, depending on which version are we talking about, like which kind of file format. They're both very similar. AIGs are more complicated because they have like binary encodings of AND gates. AAGs are ASCII readable versions, so they're larger. They're less used for software that is meant to read and kind of handle these files, so I didn't really write a parser for it because I feel like it's not needed. But once you know how to parse AIG files, you definitely know how to parse AIG files. It's a very similar idea. Then max signal is the maximum amount of nodes in the graph without the ground. So if you had 2 inputs and then 2 latches and then 2 AND gates, this would be 6, right? And it's also like it's both the sum of the 3 numbers and the highest signal in the graph. Inputs just tells you the number of inputs, and the number of inputs tells you exactly what their signals are, because they're from 1 until number of inputs. Latches tells you number of latches, but we still don't know the inputs and the initial values for each latch. In the version that was before 1.9, the initial values were assumed to be 0, and the 1.9 added the ability to kind of have an initial value, which is neat. Now, outputs is just the number of outputs, but we don't know which wires are considered outputs. Like they're connected to an outside entity, another circuit or whatever. AND gates tells us the amount of AND gates, and this also tells us like what their signals are, but we still don't know like what the inputs are. And then these 4 numbers right here are optional, and they were added in version 1.9, and they basically add some features to distinguish between outputs that we want to make sure that they're never 1. So these are bad wires. They're wires that we don't want to have 1 on them ever. Constraint wires is wires that we want to always have 1 on them. And like we don't want to consider situations where they do not have one on them. It makes sense when you're trying to model more complicated assertions. Justice and fairness, they talk about fairness constraints, and they're generally not implemented because they can be converted into bad wires and constraint wires. Like if you had an AIG file that has justice wires, you can convert it to a similar problem that does not have justice wires and fairness wires. And that's why a lot of model checkers don't even allow you to have more than zero in these numbers, or not to have them at all. Now, AIG files, latch section. The first section that we start with is a latch section. It's basically a section that is made out of like a number of lines that is equal to the number of latches, and it tells you what is the input wire of each latch and what is the initial value. Now, the initial value wasn't in version 1.9. It wasn't before 1.9, and it then was added to 1.9. So this value is optional for backwards compatibility. If you do not have it, then the default is 0, like the latch is initialized with 0. Otherwise, you would have one of the three numbers, 0, 1, or your like the same latch's wire number, which would signify that it's unknown, and it's unknown and it can be different for different latches. So that's the kind of terminology that they use. Could have used X, but I guess they just didn't like that option. So that's how it might look like. You can see here, this is the AIG file. Starts with this line right here. This tells us that it has 231 nodes. Sorry, it has 232 nodes, right? Because you have the ground, which is 0, and this is the maximum signal, which means it's included, so it's 232, but we don't talk about the 0. Then we have 34 inputs, which we already know the signals of, just because we know the number. And so they're inputs from signal number 1 until signal number 34, and then signal number 35 until whatever 35 plus 21 is. 50, 55, 54, 56. All right, 56. And then we don't talk about this, which is like I'm definitely gonna edit that out. Now, from 35 to 56, you would have just the latches, and you would define what input each latch has and what their initial value is, depending on the line. So you can see that this line right here gives us this latch, which is just latch 35, that has an input of just the ground immediately, and then the number 1 signifies that it's initialized to 1, and the output of like the output wire would be 70, right? Because this is signal 35, if that makes sense. And so the second line right here would just mean, in a very similar manner, would be 114. This is basically the input of the latch. It's initialized to nothing, so it could be either 0 or 1. And the output wire is 74, which is coincidentally what's written here, but it's because this 74 right here signifies that there's an X right here, if that makes sense. Okay. Now, this 152, we can see that the 0 is redacted, because you can do that, because that was before 1.9. And so you have a latch which is 152 with 0 as initial value, and the wire number would be 80. That's the output wire. All right. Now, output section. This is basically after we have the latch definitions, we start talking about which wires are considered output, and so it would be just basically like a number of lines. Like if you have 7 outputs, then you have 7 lines. On each line, there's a wire number. A wire number is anything from 0 until the maximum signal times 2 plus 1, right? Because you can have you have the maximum wire number, and it can also be negated. So that's the span that you're allowed to be in. And that's it. It basically tells you what are the outputs of the circuit. Previously, this was used as basically what you want to verify. These were considered like bad, bad wires, meaning wires that you would never want one on, and then that would be the problem that you're trying to prove. Um, but then they wanted to like differentiate between bad and constraints, so they just added other kind of wire definitions, bad and constraints and whatnot. Um, but it's generally very possible to do all the things you want to do just with output sections, and basically the software that I implemented thus far does this. It just considers like graphs that have an output, or um, it doesn't matter if it's a constraint or a bad or an output, whatever you want to call it. It's for me, it's a wire that I never want one on, and that's fine by me. Now, after that, you would have like a bad wire section, also very similar. The amount of lines should be the same amount as bad wires, if bad wires exist since above zero, and then we just list what bad wires are, and so on for constraint, and even justice and fairness. Now, a note about justice and fairness, all these things, I talked about this before, they came in version 1.9. A note about justice and fairness is that a lot of model checking software don't even allow AIGs that have this, because it can be translated, and you should do that once and then never do it again, because apparently it's not simple, but it's polynomial in time, so it's not a problem that you need a model checker for. And now, let's talk about AND gates. So AND gates are difficult. All right. After all the sections that came before AND, we have a section that talks about AND gates. And this section is actually written in binary. So I'll show you the file soon. You'll see that it's not even readable by VS Code. Why? Because it's just a series of bytes. The reason this was chosen to be a series of bytes is because you might have almost a squared amount of AND gates, or even more, for the amount of latches and inputs. So like for a 1,000 inputs and 1,000 latches, you might have something like 1,000,000 AND gates. And so the smaller the AND gate representation is, the better. So AIG files has this binary encoding. AIG files have basically also just lines with 3 numbers on them, the signal of the AND gate, and the 2 inputs. That's kind of the major difference between them. There's another difference that signals can be whatever in AIG files, but in AIG files they're very well defined. You start with inputs, then you go on to latches, then you go on to gates. But that's not true. That's not true for AIG files. And it's. Let me get started. So this is an AND gate, right? We call this the left-hand side and this right-hand side. Typically, I think about it in the opposite, like an opposite way. I think about the AND gate going to the right, actually. But this is the way that the presenters of the format talked about it, and so I'm just gonna do this for simplicity, not to get confused with other stuff. Anyways, so look at this following AND gate. We know that both right-hand sides should be less than left-hand side, like not even equal, just strictly less, because otherwise we can't guarantee that there is no cycle, and in legal circuits there is no cycle in AND gates. So this is fine. This is a correct kind of something that an AIG file, a legal AIG file, should always adhere to. Furthermore, we're gonna assume that we have these two inputs, and right hand side is greater or equal to right hand side 0 is greater or equal to right hand side 1, and this is without loss of generality. It doesn't matter, one of them has to be greater and equal than the other. And so any file you want to write down, you just take the greater one and then make that right hand side 0. Okay? Now, we already know left hand side. Why do we know it? Because we know how many AND gates there are. And since we know how many AND gates there are, we can simply know that the first wire number for the first AND gate would be number of inputs plus number of latches plus 1. And then so on and so forth. It's kind of similar to what we saw before. Just by knowing the number of inputs, latches, and AND gates, we can know what are the ranges that they all fall into. Now, this means that so all we need to store is right-hand side 0 and right-hand side 1. The reason why we don't store them directly is because they can be kind of big, so we use another trick, which is basically, instead of storing them, we store the differences between left-hand side and right-hand side 0, and the difference between right-hand side 0 and right-hand side 1. So these are delta 0 and delta 1 here. Okay? And this is better than storing the original ones because these are smaller. Like, they're actually smaller numbers, not like smaller in size. But when we encode them, the encoding kind of mechanism that we use gives a strong advantage to smaller numbers, meaning that we use a lot less bytes to store smaller numbers. So we can always encode a series of U38 numbers by giving 4 bytes for each. This we already know. If you have or you should know at least, if you have 4-byte numbers, you can just give 4 bytes to each one, and then the binary section can just be like a series of 4 bytes, 4 bytes, 4 bytes, whatever. But here we do something a bit more smart. We use kind of dynamic encoding. We take the MSB of each byte, and if it's 1, that means that then the byte that's after it is part of the same number. If it's 0, it means that that's it. It's kind of like a null value in a linked list, which means that there is no next. That's it. This byte ends the current number that we're trying to write. And then the other 7 bits are basically part of the number. And the ones that we read first are the ones that are part of the least significant side of the number that we're building. So if I were to take a hexadecimal as, I don't know, A55A, for example, in binary this would be something starts with 1 here, and then 7 bits, and then 0 here, and then another 7 bits. So we know that this is one number, because we read the first byte, we see that the MSB is 1, and so we know that the next byte is part of the same number. All right? And so we take them, and then we flip them. The reason why we flip them is because the first one that we read, we know that it's part of the least significant portion of the number. The second one that we read, the 7 bits here, are more significant. And so we put them to the left. This can be done using simple bit shifts, so it's very, very simple. And then we just convert this number to decimal, which is it's really not even an operation. In binary, it just works out. And then this is the delta 0 that we would get with delta 1. These are the differences. And so we can figure out AND gates from this. And I put in an example here to actually solidify this fact right here. So if you saw a string of bits, or a string of bytes that looked like this in hexadecimal, we look at it in binary, and then we see each time that we have a 0 in an MSB, we know that this is the last number that needs to be in the current number that we're trying to model. So here I switch colors between blue and green, and so we can figure out each time where the number kind of changes. So here we start with a 0, and so we know this is the last number, and so the first delta would be just 1. And it's literally left-hand side minus right-hand side. And so we can figure out literally what the right-hand side what the first right-hand side is for the first AND gate. So we take the other number, we see the MSB is 0, so this is it. We don't need to read anymore. And then we figure out that from the other 7 bits, we figure out that the number is 0, and then we just say, the second delta is just 0, so right-hand side 0 and right-hand side 1 are basically the same, so it's just an AND gate that has 2 inputs that are the same. Completely normal. Now, we move on. Same thing for here. The MSB is 0, so we take these 7 ones, and that gives us 127, which is delta 0. And here we have the first case of an MSB, which is 1, so we have to read the byte after it. And then this MSB is also is now 0, and so we know that we're done. So these two numbers together, we take these three zeros. They're part of the least significant portion of the number. And then we take these 6 zeros and the 1, we put them right here, and then we get the number 128. And similarly, we move on. Like here we have a 1, so we take these two bytes. Here we have, for example, in this portion, we have 1, 1 again, and then 0, which means that this is the number that we're taking into consideration. And, similarly here and here. And just notice that, like, we're taking the MSB, the least significant portion. Sorry, the least significant portion of the number would be the thing we read we read prior. Okay. No, the thing we read first. Sorry, the thing we read first is the least significant portion, and then every extra byte we are basically adding to the left of the number. Okay, so this is done by a mask and some bit logic, but it's doable. Okay. So there will be two numbers for each gate, right? But they're typically small numbers because the differences between inputs would generally, in most, like in testing, is actually small. And so we get a significant advantage in using this format in the sense that it uses way less space. Yeah, the two first deltas correspond to the first AND gate, the two second deltas correspond to the second AND gate, and so on and so forth. This is how the file looks like, and as you can see, it's binary, and so some of the bits, the bytes do not encode legal ASCII characters that VS Code can show, so it doesn't even bother. Now, we move on to a symbols section. We're allowed to add a symbol to each node that is either an input, a latch, an output, a bad, like wire, or a constraint, a justice wire, a fairness wire. We're allowed to add symbols to these nodes, and the way we do this is via a symbols section that basically you have a letter, then you have the signal number, wait, not the wire number, the signal number, and then just a space and whatever ASCII string you want. This is how it might look like. So here we have I0 and just like a string. So input 0, then a string. This is interesting. Hold on. Because input 0 is not a legal yeah, no, not the signal number. There's a mistake here. I'll correct it and possibly redo this, but it's not the signal number. It's actually the index of the input or latch or whichever wire you're saying. Like if you said, oh, the first input, and so you know what the wire number of that thing is, or what the signal is, and so you could just give that a string value to actually add to that node. And that's how this basically works. It's very simple, and this is not really important for model checking. It's just neat to add to AIG files. Now, a comment section is just a simple section that you add to the end of the file. It starts with a C, and everything after the C is basically just whatever you want. So here we have, I used a model checking software called ABC, and I used it to turn AIG files into folded AIG files, which basically means that I take constraint wires and I rewrite them into the bad wires, and then if I solve the case with the folded, that is like it directly means that the case without the folded file is the same. Basically, what this means in general is that you get rid of constraints by just adding extra constraints by adding extra logic to the circuit, and adding that logic into the bad wires. Okay, if you understand what constraints are, then I can go deeper into basically what this is. But it's not a big deal. You don't have to know about it. I'm just saying that after I used it, ABC adds some kind of stamp that it wrote this file, and so this is a comment that it adds. Quite neat. Thank you. That was it. That was how AIG files are. I hope I gave enough like background information about what everything is. After you see this, you understand. Okay, so the problem is it's quite, it's well defined. That you're given a file that looks like this, and all you're trying to say is there a sequence of inputs that leads to a one on a bad wire, or if you don't have any bad wires, then we're talking about the old format. So it leads to a one on one of the outputs, right? That's it. Is there a sequence of inputs that leads to one of the outputs? Now, there's a continuation of this that takes these files and takes these, kind of structures and turns them into something that has to do with logic and SAT solving and all these things. This is something for a later video. Thank you for listening.